Hello everyone and welcome back to Sky Scholar. My intention had been to move on to the second solar spectrum for the group 2A elements. However, I decided to divert slightly and examine relative abundances of elements in the Sun. That will help us to place our results in better context when we move back to spectroscopy. Yet before I begin discussing the solar abundances, I wanted to pay tribute to two well-known solar physicists. First, I wish to begin by remembering Charlotte Moore. She was one of the great foundational figures of modern astronomy and played a pivotal role in the characterization of spectroscopic lines. Her Multiplet table of astrophysical interest is an absolutely incredible work. I have linked it below and I encourage everyone to go to the file and have a look. It is simply astounding that one person could have produced such an impressive compilation. Clearly, science is built on the shoulders of giants. Progress is made because someone took the time to examine the details. If you care to learn about Charlotte Moore Sitterly, I have provided several links below. Next, I wish to mention Professor Robert J. Rooten, who passed away just a few weeks ago on September 28, 2022. Professor Rooten was an emeritus solar physicist at Utrecht University and the University of Oslo. He was a recognized authority in solar spectroscopy and spent many years teaching graduate-level courses. He took the time to make the lectures available online in the form of his Compendium Solar Spectrum Formation, which is linked below. In his own words, this compendium contained everything he knew about solar spectroscopy. Now, for those of you who wish to learn about this subject, this is an invaluable resource because it tackles the problem in detail. Most importantly, the compendium provides literally hundreds of freely accessible links to spectra, documents, and papers, which form the foundation of what is accepted today in solar physics. Of course, for my part, I wish to change much of the way we think about solar spectra. Nonetheless, I recognize the importance of men like Professor Rooten because his compendium provides an encyclopedic level of detail, even if some of it must eventually be modified. Thus, if you have some formation in spectroscopy, physics, or chemistry and are interested in solar spectra, this compendium is a wonderful resource which I encourage you to study. If you devote the needed time, you will gain graduate-level experience in solar spectroscopy. Now let us move to photospheric relative abundances. Here is the table of modern relative abundances for a few atoms provided online by Katharina Lodders. As we had discussed in this video, modern solar abundances are determined by examining solar spectra and by noting the distribution of elements in meteoric chondrites. There is actually no scientific basis for such reasoning, as we can never be certain of any real link between the chondrites and the Sun. In determining relative abundances, we can also have recourse to the solar wind, as can be gathered in these two papers. Unfortunately, not all elements are equally likely to be present in the solar wind. Some may be preferentially retained or expelled by the Sun. This makes all determinations of solar abundances from solar wind measurements of limited value. They do tell us something about the solar wind, but are simply not relevant to what is happening in the photosphere or within the Sun itself. All photospheric relative abundances we determine could be very far removed from what has actually taken place. We cannot know if the spectroscopic contribution of any given atom has been either amplified or attenuated as a result of interaction with solar material. We are only guessing that the values have importance when in fact they could be irrelevant relative to the true distribution of elements. In any case, it is instructive to highlight how relative solar abundances have changed over the years. This serves to emphasize how much these values can fluctuate and how little importance one should place on relative abundances. In order to accomplish our goal, we can calculate comparable values by referring to Henry Norris Russell's work on the solar photosphere. This classic paper was published in 1929. By examining Russell's work, we can get an idea of how values have changed over the past 100 years. As a small piece of history, Charlotte Moore was a major contributor to Russell's efforts and was employed for many years in his laboratory at Princeton. In order to convert Russell's numbers and relate them to modern values, a couple of steps need to be taken. First, Russell provides two columns for relative abundances in his table 14. The first is for the neutral atom and the second is for the ionized atom. These must be summed to provide us with a total relative abundance for a given element. Since these are logarithms, the sum is performed in this manner. For instance, Russell provides a log of natural abundance for neutral hydrogen of only 11.2 and 5.7 for the ion. That results in a total relative abundance for hydrogen of only 11.2. For hydrogen, the neutral atom dominates. We then add 0.8 to this number to bring the value up to 12. In this manner, all of Russell's values can be related to modern measures. In order to convert numbers for the other elements in Russell's table 14, we simply use this equation. I do not list all of the elements in the table, just a few to make the needed points. To begin, Russell does not provide us with a value for helium. That is because he has no way to properly ascertain it. That remains true today, even if astronomers claim that the Sun is about 10% helium, according to their accepted relative abundances for this element of 10.924. Now, if you study Lodders' paper, you will see that this value is derived from helioseismology. Yet, as I have argued long ago in this video, seismology is a science of condensed matter. The idea that one can extract helium values from seismological measurements is not reasonable. One has absolutely nothing to do with the other. Now, to help bring the point home, examine the value in the table for oxygen. This is thought to be the third most abundant element in the Sun, with a modern relative abundance of 8.71. Russell had provided a very similar number. Using our handy equation, Russell's value actually comes out to 8.8. One would say that the numbers have not changed too much. But now let us consider this paragraph from the solar physicists relative to changes in oxygen abundances and helioseismology. The solar chemical composition is still under debate. The case for oxygen, the third most abundant element in the Sun after hydrogen and helium, being particularly important. One of the traditionally accepted abundance sets considers an oxygen abundances of log epsilon oxygen equal 8.93 plus or minus 0.4. In the usual astronomical scale referring to hydrogen, where log of epsilon oxygen is equal to the log of the number of the element divided by the number of hydrogen plus 12. This abundance was later downward revised to log of oxygen equals 8.83 plus or minus 0.06. With this abundance set, there is an excellent agreement between solar interior model predictions and the helioseismology. However, using more recent three-dimensional theoretical models, lower solar metallicities have been obtained. For example, Epsilon et al. Reach log of oxygen equal 8.66 plus or minus 0.05, which may spoil the agreement with the helioseismology. Note, however, that a recent study suggests that we might be underestimating interior opacities, which could restore the agreement with helioseismology. Given that oxygen is a very important element for stellar interior models, adopting such dramatic revisions would have implications over a broad range of topics in astrophysics. Note how they have saved the day. We could be underestimating interior opacities. In reality, they have no idea about interior solar opacities. Now, one can see the level of faith involved. For tiny changes in the oxygen abundances, the entire field of helioseismology needs to be reconsidered. You can be certain that as a result of all this, reviewers will be very careful not to allow anyone to significantly alter accepted relative abundances for any element. We will become locked in a scientific paradigm without real justification. In any event, we will never know the opacity values inside the Sun, and claims to the contrary are not scientific. I have already stated that the Sun is condensed matter, that seismology is a science of condensed matter, and that solar opacity values derived by the astronomers have no relevance to the real solar interior. You can read more about this in this paper. Now that we have seen the effects that a small change in oxygen relative abundances can have on modern solar theory, have a look at how relative abundances have changed in the rest of our table. We begin with lithium. You recall in these two videos that lithium might help stabilize the lattice of a metallic hydrogen sun. As such, it would not be unexpected that the detection of lithium might be difficult in the Sun relative to its known concentration in the chondrites. In the last video, we saw how the lithium line is enhanced in the second solar spectrum. So what has happened to our lithium values over the past 100 years? Well, the calculated value for Russell is 2.5. That compares to an accepted modern value of 1.04. So the relative lithium abundance in the Sun has decreased by a factor of nearly 30. Next, have a look at carbon. The modern value is 8.47. The value calculated using Russell is only 7.3. Thus, the relative carbon abundance has increased by a factor of 15. Wow! Imagine what that means relative to what we just saw with oxygen. Carbon, after all, is a significant atom in the photospheric spectrum. It is not like lithium. Next, have a look at sodium with an accepted modern value of 6.21. The computed value from Russell is 7.7. So the value for sodium has decreased by a phenomenal factor of 30. Then we come to sulfur with an accepted modern value of 7.15. The value calculated from Russell is 5.6. As a result, the relative abundance for sulfur has now increased by a phenomenal factor of 35. As for potassium, it has an accepted modern value of 5.04 and the value derived from Russell is 7.3. Therefore, the relative abundance for potassium has now decreased by an absolutely phenomenal factor of 181. I list the values for the rest of the elements in the table and also place the factors of change relative to modern values. Note that the relative abundance of iron, an element with important lines in the Fraunhofer spectrum, have now increased by a factor of 11 compared to the values obtained from Russell. The point is made, in what other area of science are observationally determined numbers changing to such a degree? It is true that we have more information now about the Sun than we did in 1929. We can monitor coronal lines in the ultraviolet and X-ray using satellites in a manner which Russell could only dream of. The same can be said about solar winds. But that does not account for changes in the relative abundances of lithium, carbon, sodium, sulfur, and potassium. The problem remains that all of these methods are subject to the same sources of error. We can never be sure of these measurements because we do not fully understand the elemental chemistry or coordination involved in the atmosphere of the Sun. To compound the problem, solar physicists are restrained by their models and what they envision as taking place in the Sun. If an observation does not make sense, then they simply discount it. We will go over this in the next video when we discuss the beryllium lines. In any event, that is all for now. Next we will move to the analysis of spectroscopic lines in group 2A elements, namely beryllium, magnesium, calcium, strontium, and barium. These elements are important because they love to make hydride molecules in the laboratory, and there is plenty of hydrogen to make this possible in the atmosphere of the Sun. The group 2A elements are also among the most important contributors to the Fraunhofer and second solar spectrum. In any event, if you enjoyed the video today, promote the channel, mention the videos to your friends and to your local astronomy club, support me with a like, and subscribe for more videos as we look more closely at the Sun, the stars, and beyond. Comments are always welcome down below, and I'll see you soon on the next video.